Hi, Hans here, plcskilltree.com. Did you know that nowadays shift registers are used everywhere in modern production facilities? And there's a good reason for that. You see, as manufacturing gets more automated, more data-driven, shift registers are essential to keep track of every box, every product, every item moving down a production line. In today's tutorial, I'm going to show you exactly how shift registers work, and I'll be using a real-world example from a bottling line with 7 processing stations. It's going to be very exciting. Here's what we'll cover. First, we're going to talk about what a shift register actually is and the 3 key components that make it work. Then we'll have a look of how it fits into a real-life bottling line with multiple processing stations. And finally, I will share with you how all of this translates into modular, scalable PLC logic inside TIA Portal. Just a quick heads up before we jump in, the shift register example that I'm sharing with you today is based on a fully downloadable template that I've created for TIA Portal. It's very straightforward. You download the TIA project, you follow the step-by-step guide that comes with it, and you copy over the blocks, the data types, the logic to your own PLC application. Just like that. Simply hit the link in the description below this video to grab your copy of the shift register template. Alright, enough with the introduction. Let's get structured with shift registers in TIA Portal. Okay, so let's start at the beginning. What is a shift register? A shift register is a layer of software that you add to your PLC application and that tracks items as it moves along a conveyor belt or a conveyor chain. It does this by shifting data from one position to the next, matching the physical movement of the actual products on your line. So as each product moves forward, its associated information moves with it, step by step through the line. In a PLC program, a shift register is built using an array. Each element in this array, each physical product on your production line, is represented by a block of data. This data shifts periodically to reflect the physical movement of that product. So those are the 3 core components of a shift register: the array, the data, and the shift. Let's have a closer look at each one of them. From a big picture perspective, a shift register is really just an array, where each element represents a specific position on your production line. Here's an easy way to picture it. Imagine you've got a conveyor belt, and that belt is divided into zones of equal length. And let's take an easy example. Let's say we have 7 zones, starting from zone 0 to zone 6. Now each zone can either hold a product, hold a bottle, or it can be empty. And each of these zones, each of those physical positions on your conveyor belt matches up with the position in your shift register array. Now as a conveyor moves forward, the data in your shift register moves along with it, keeping track of each product as it moves from one zone to the next. It's a straightforward way to map real-world movement to data inside your PLC application. Next up, let's have a look at the data. And this is where most PLC programmers miss the ball. You see, most PLC programmers are used to simple arrays like an array of integers or an array of reals to represent the data of each product on their conveyor belt. But here's the deal. The clearest and most scalable way to represent data of each product in your shift register is by creating a user-defined data type, or in short, a UDT. A UDT keeps your data specific, which means you can clearly define the variables used in your structure. It's modular and easy to maintain. Change the structure in one place at the UDT level, and it updates everywhere in your PLC application after compilation. Perfect if your line grows with more modules or you need some additional data afterwards. Now the exact contents of your UDT, that depends on what your application needs. But at a high level, the structure of your data should match what's actually happening on your production line. For example, if your shift register is part of a bottling line with 7 key stations: in-feed, cleaning, filling, capping, labeling, inspection, and reject, then you start by building a user-defined data type. Let's call it, for example, UDT SR data, and you populate that UDT with the same 7 processing stations as substructures. Each element in the array represents a specific position on the production line and also serves as a data container for all processing information related to the product at that position. So if we use our bottling line example again, as a bottle moves along the line, each station like in-feed, cleaning, filling, capping adds its own data to the array element that matches the bottle's current position. So when a bottle reaches position 1, The infeed station processes that bottle and updates the infeed section of the data structure at position 1. A couple of shifts later, that same bottle reaches position 3, the cleaning station. At that point, the array element at position 3 already contains the infeed data from 2 steps ago. Now the cleaning station processes that bottle and it adds its own process results and data to the cleaning section of the array element at position 3. The bottle keeps moving down the line, passing through each processing station one by one until it finally reaches position 12. By that point, the array element at position 12 holds a complete step-by-step record of everything that's happened to that bottle along the way. Now you're probably wondering, what kind of data should I include in the shift register for each station? Well, every process on the line, whether it's infeed, cleaning, filling or capping, usually tracks 2 main types of data. First, there is the process data. This is general process information like, did the process succeed? Did something go wrong during the process? And maybe a timestamp for that success or fail event to know when it happened. Then you've got process-specific data. And this is where each station gets to record its own unique information. Like at the infeed, for example, you might want to write a unique bottle identification number for each bottle. Then when that bottle makes it to the filling station, you could track how much liquid was added or whether the filling caused too much foam. And here's a little insider tip. It's a great idea to include a general section in your UDT. Think of it as a quick status overview. Basic stuff like whether a bottle is present, if everything has gone smoothly so far, or if a reject code was triggered. That kind of general overview data gives you a quick snapshot of each product at any position on the line and makes it super easy to set conditions for the next station down the line. Now that we've covered the array and the data, let's have a look at the final piece of the puzzle, the shift. The shift is what keeps your digital world in sync with the real one. Every time the conveyor moves the products one spot forward, the shift register does the same. It shifts all data elements in the array one position forward. Now there are 3 popular ways to trigger a shift: using a virtual position window, using a hardware sensor, or handling it purely through software logic. Let's take a closer look at each one of them, starting with the position window. Many modern production lines like chain systems or conveyor belts, they use servo drives to move products. And often these servo drives are controlled by a virtual master axis. That's basically a software controlled axis that all the physical axes follow, keeping everything perfectly in sync. A typical setup is to have a virtual axis move cyclically between 0 and 360 degrees at a given speed. Now you can define a position window, for example from 50 to 80 degrees, and each time the virtual axis position hits that window, the shift register moves one step forward. It's clean and reliable and there's no dependency on any physical sensors, but it does require you to have a virtual master axis in your application. Another classic method of shifting a register is by using a hardware sensor. Here you typically mount a sensor on the conveyor or on the chain to detect something repeating like a pin, a hole or a notch, and each time it sees that marker, it triggers the shift. This method is simple and reliable and it doesn't require any fancy motion control like a virtual axis, but it does need some hardware and some wiring to get it up and running. Finally, you can trigger the shift purely through software logic. For example, if your line is running and all your product processes are done, you shift the register forward. No sensors, no virtual axis, just logic. You just gotta make sure that your software conditions are bulletproof. If your logic fails, your shift register won't shift correctly. Alright, now that we've got the shift register basics covered, let's see how all of this works in a real-world bottling line example. Picture a line with 7 stations: infeed, cleaning, filling, capping, labeling, inspection, and reject. As bottles move from one station to the next, the shift register keeps track of every step. Before we dive into the actual PLC application, let's quickly look at this real-world setup and let's see how each of these 7 stations use the shift register for automating the bottling process. Module 1, infeed station. This is where the shift register kicks off bottle tracking, right at position 1. The infeed station uses a sensor to check whether a bottle is present. If it is, it logs that info along with a unique bottle identification number into the infeed section's data segment at position 1. And it also updates the general section with the same information. Once the infeed check is complete, it writes a process done flag along with a timestamp to the result segment of the infeed section. The conveyor now moves forward 2 steps, bringing our bottle to module 2, the cleaning station. At position 3, the cleaning station checks the general section of the shift register to see if a bottle is actually present, based on what was detected at the infeed 2 steps ago. If there's a bottle, the cleaning process starts, and if not, it skips the station. Obviously, if there's no bottle, there's no need for cleaning. Once cleaning is done, it writes a process done or process failed status, along with a timestamp to the result segment of the cleaning section. It also logs cleaning specific details like applied spray volume, spray temperature and drying time to the data segment. If the cleaning fails, the general section gets updated with a reject flag and a reject reason, so it's clear why this bottle was marked as a reject. After the conveyor moves 2 more steps forward, the bottle arrives at module 3, the filling station. At position 5, the filling station takes care of accurately getting liquid into the bottles. Depending on the product, this might be achieved using gravity, pressure, vacuum, or piston filling. The filling process is only allowed if there's actually a bottle at position 5 and this bottle hasn't been marked as a reject, which basically means it passed the cleaning step that came before it. After the filling process is complete, it logs a process done or process failed status with a timestamp to the result segment, and it records details like fill volume and which valve was used in the data segment. If filling fails, the general section is updated with a reject flag and a reason, making it clear why the bottle was flagged as a reject. Right after filling, the bottle moves to the capping station at position 6. This is where a cap gets placed, whether it's a screw-on, snap fit, corked, or whatever the product calls for, and torque control makes sure it's tight but not too tight. Before doing anything, the capping station checks the shift register to confirm that everything's gone smoothly so far. That means the bottle needs to be present and it must have successfully passed the previous stations. Once capping is done, it logs the result, process done or process failed, along with a timestamp to the result segment. And it records details like cap type and applied torque in the data segment. If something goes wrong during capping, the station updates the general section with a reject flag and a clear reason why that bottle was rejected. Next up, Module 5, the labeling station. At position 8, labels go on. This module handles all kinds of labels, adhesive, shrink sleeve or glue based, and it makes sure that the labels are aligned correctly. Just like the previous stations, it first checks the general section of the shift register to confirm the bottle is present and has successfully passed all prior steps. Once labeling is done, it updates the labeling section at position 8. The result segment gets a status and a timestamp, and the data segment logs details like the label type and vertical placement. If labeling fails, the general section is updated with a reject flag and a reason so it's clear what went wrong. The conveyor belt moves 3 steps forward, and at position 11, the bottle arrives at the inspection station. This is where quality control kicks in. Vision systems, sensors and detectors check everything from fill levels, cap fitment, label placement, to the overall condition of the bottle. Just like the other stations, inspection only runs if the bottle has made it through the previous steps. So it starts by checking the general section at position 11 to make sure a bottle is present and hasn't been rejected yet. After inspection, it updates the shift register with the result, a timestamp, and inspection-specific data like the barcode readout or whether the fill level and cap placement were okay. If something goes wrong during inspection, like an error with the vision system, the general section gets updated with a reject flag and a clear reason why using the reject code. 6 stations done, 1 more to go. Finally, the bottle reaches module 7, the reject station, at position 12 in the shift register. This station works a bit differently from the others because it only executes when a bottle is marked as a reject, whereas the other stations run if the bottle is not rejected. So before starting its process, the reject station checks the general section at position 12 to see if the bottle is flagged as a reject. And if it is, the station removes the bottle from the line using a pusher, an air blast, or a diverter arm. Once the reject action is completed successfully, the result segment is updated with a process done flag and a timestamp. The data segment is also updated to record whether a manual reject was performed, like an operator pushing a button, and which reject reason was registered during removal. Alright, That's the full rundown of all the 7 processing stations. Each station reads from the shift register to decide if it should run its process, and once finished it writes back whether the process was done or failed, along with a timestamp, a reject code if needed in case it failed, and process station-specific data. Using a shift register, we can track exactly what happens to each bottle as it moves down the line. And remember, every time the bottles move one physical step forward on the conveyor, the data in the PLC's shift register shifts right along with them. Are you ready to see how all of this shift register magic translates to an actual PLC application in TIA Portal? Let's dive in. Like I mentioned in the beginning of this video, if you want to dive deeper, you can grab the full PLC application I'm about to show you as a downloadable template. It includes the PLC application and a full step-by-step guide that walks you through the entire shift register setup and how it all integrates into a 7-station bottling line. You simply open the PLC application, copy the UDTs, DBs, library blocks, and logic to your own application, and you're good to go. So don't wait, click the link below, download the template, and start exploring the full bottling line logic right now. Alright, let's take a closer look at how this PLC application is built. I've broken the application down into 5 main sections to keep things clean and easy to navigate. First up, the machine section. This section handles the overall machine control. Modules like the state handler, recipe management, and the main shift register logic all run from here. Next, the equipment section. This is where the process logic for each of the 7 bottling stations goes. Each module has its own function block, its own logic, and runs independently. Then we've got the global data section. All the shared data blocks, all the shared data used throughout the program are stored here. The library section, that's where all your reusable function blocks go. And finally, organization blocks. That's for startup routines, error handling, and interrupt tasks. Now, before we have a look at how the shift register fits into all of this, there's one important thing you need to understand. There are 2 main parts to integrating a shift register into an existing application. First, we've got the shift register data array and the core logic that handles shifting the data elements forward or backward, including the configuration for the trigger. This main logic is built into the PLC application as part of the machine modules. Secondly, we have station-specific logic, including dedicated library blocks for shift register specific tasks. This is where each station reads from or writes to the shift register. Like for example the filling station, before it fills a bottle, it checks that cleaning was done successfully. That logic is handled under the equipment section, inside the function block logic for each station individually. In this part of the video, we'll look at the core shift register logic and how the data structure works, and then in the next section, we'll see how each bottling station talks to the shift register through its own logic. The shift register itself is an array made up of multiple elements all sharing the same user-defined data type. In this template, the array is declared in the data block DB shift register, which is situated right here in the machine section of the global data program group. In this DB, I have declared an array called data with 21 elements, indexed from 0 to 20, and all using the same user-defined data type, UDT SR data. Each element in the array follows the same data structure. This structure includes information for all 7 stations of the bottling line, plus a general section that tracks overall bottle information, such as whether a bottle is present, a reject flag and a reject code, and a unique bottle identification number. So that's it for the actual data of the shift register. Now the logic that shifts all that data forward or backward can be found under the machine section of the application. In the function block FB machine module, that's what the MM stands for, shift register. We've got 3 networks here in our block. The first 2 are just for setting up which signal we want to use as our forward or backward shift trigger. Like I mentioned earlier in the video, this trigger can be a virtual position window, a hardware sensor, or software logic. In this template, I am using a virtual position window as the forward trigger, and that signal is actually defined inside the conveyor control block. The backward trigger is not used here. Then we get to network 3, where the real action happens. This is where the block is called that handles the shifting of the data. It's a library block, which just means it's self-contained and reusable. So if you got more than one shift register in your project, you don't have to rewrite anything, you can just reuse this block. You'll find the block itself over in the library section of the project. Now if we take a closer look at the block call in Network 3, there are a few things to highlight. The forward and backward triggers are set as input parameters right here. Then we've got the shift register control structure called IQ-ST-control, which is declared as an in-out parameter. This contains all configuration, command, status and fault parameters to operate the shift register. Next up is IQ-ST-data, which is the actual shift register data. It's also passed through to the block as an in-out parameter. And here's a little insider tip. When you're working with large amounts of data like arrays, UDTs or strings, don't use the input or output parameter. Use the in-out parameter instead. It saves system resources because it just passes a reference of your data to the block instead of copying all of that data. Finally, over here on the right side of the block, you've got status outputs, like whether the shift register is currently shifting forward or backward. Super useful when troubleshooting this block online during runtime. Now let's go ahead and open this block and check out what's going on inside. Right at the top in the block interface, you'll notice that the shift register data, the IQ-ST data, is declared as an array with dynamic size. That's what that little asterisk means between the brackets. And this is really awesome because it means you don't need to edit the block every time you want to change the size of your shift register. The block automatically adjusts to whatever array size you feed it. Super easy and super flexible. Now if we take a quick look at the networks. Network 1 is where we read out the size of the array. Since we're using a dynamic array, we need to know how big it is, we need to know its size, before we do any loops or any indirect addressing with it. I've created a separate library block for getting the array size, so you can reuse that block anywhere else in your program if you need to. Network 2 reads the trigger signals from the input parameters and writes them into the control structure of this shift register module. And this is just a good solid habit to get into. Writing important signals, important sensors, counters, steps into the data structure of your module makes life so much easier when you're monitoring the module or you're setting up a data trace later on. It keeps all important module information organized in one place. Networks 3 and 4 is where the magic happens. This is where the shift register actually moves forward or backward. When we get a forward trigger, we run two move block variant instructions. The first one shifts all the data one step forward, and the second one copies a new initialized data entry at the start of the array, position 0. Network 4 does the same thing, just in reverse. First, it shifts everything one step back, and then it adds a fresh data entry at the end of the array. A quick reminder here. All these array-specific instructions like the move block variant instruction and all shift register specific library blocks are explained in full detail within the downloadable template. So check out the description below this video for more information. Next up, networks 5 and 6 handle some basic status signals for the shift register control structure, like whether we're shifting forward or backward. There's also a shift counter in there that goes up with every forward shift and goes down with every backward one. Finally, networks 7 to 11 take care of information outputs that you can read straight from the outside, from the block call itself, and this is great for troubleshooting the block without having to open it. So that's pretty much it for the core part of the shift register, the data itself and the logic that does the actual shifting. Now let's jump into the fun part. Let's have a closer look at how each of the 7 stations on the bottling line uses the shift register in their own process logic. Alright, quick recap. The 7 stations in this bottling line example are infeed, cleaning, filling, capping, labeling, inspection, and reject. You'll find each of these as separate modules in the PLC application, all grouped nicely under the equipment section. Each station is handled by its own function block, which keeps the whole setup modular and easy to maintain or scale later on. Now, each of these modules has its own little set of configuration data, and all that gets initialized in a function called config equipment modules. If we open that up, First thing you'll notice is that I'm not using ladder logic here. We're writing an SCL or structured control language. This is very close to structured text, and it's very easy to read when you're just listing parameters with their configured values. In this configuration file, each module, each station, has a dedicated section where we assign a specific shift register position to each one. For example, infeed is at position 1, cleaning is at position 3, and so on. This configuration setup gives you a lot of flexibility. It makes it easy to reuse the shift register logic on other production lines that might have a different station setup. Like maybe your infeed is not at position 1, it's at position 2, or maybe your line doesn't even have a cleaning station, or it has 2 of them. Whatever the setup, you can configure it right here in the configuration file without changing the core shift register logic. Now let's have a look at how shift register logic is integrated into each processing station. Let's open, for example, the filling station right here, FB Equipment Module Filling. This block is split into 6 clear network sections: reading from the shift register, sequencing, fault handling, status signals, writing to the shift register, and output logic. Networks 1 and 2 are all about reading data from the shift register. In Network 1, we're just doing a quick plausibility check. We're making sure that the configured shift register position for this station is actually inside the array limits. There's no point reading from an array element that doesn't exist, right? Then in Network 2, we define the shift register conditions required for processing the bottle at that specific station, in this case, the filling station. There's 2 simple checks here. 1, the bottle has to be physically present, so the bottle present flag needs to be true. And 2, it shouldn't have been rejected earlier, so the bottle reject flag needs to be false. If both are good, we're clear to move on and let the station process this bottle. Networks 3 to 5 handle all the sequencing steps for the filling process. First, the station checks some basic flags like a start trigger, if the module is selected on the HMI, production line is running, and there are no errors. Plus, the shift register needs to confirm that the bottle is good to go, meaning bottle present and not a reject. Once the station finishes everything without any issues, meaning it's not busy anymore and no errors occurred during processing, it sets a process done flag. That flag is what triggers the writing of process results to the shift register later on, and it basically tells the shift register, yes, this bottle was filled successfully. The next 7 networks take care of fault handling for the station and writing status flags like module error. The following 3 networks are where the station writes process results and process-specific data back to the shift register. First, we figure out why a process might have failed. This happens in the first network of the write section, where a fail code is set that we later use to determine the reject code in the shift register. In this example, there are 2 possible failure reasons. Fail code 1 if the filling station wasn't enabled via the HMI, or fail codes 10 to 14 depending on which fault happened before or during the filling process. If any of these failures occur, the process failed flag gets set. The second network takes care of writing the general process results to the shift register, whether the process finished successfully or failed, along with a timestamp. This write action is triggered by either the process done flag or the process failed flag, and is handled using a reusable, self-contained library block. The last network in this section writes process-specific data to the shift register, but only if the process completed successfully. Depending on your application, you might also want to log process-specific data even when the process fails, especially if detailed data collection or diagnostics are required. For example, at the filling station, the following data are written to the shift register: whether foam was detected or not, the actual filling volume, and which valve was used for filling. Finally, in the last 2 networks of this filling module, we write information outputs, like whether the module is selected or faulted, and the current sequence step of the module. And that wraps up this tutorial on shift registers, what they are, how to build them, and how they fit as a powerful automation layer right inside your TIA project. So I hope this video gave you a clearer understanding and a boost in confidence to tackle shift registers on your own. If you want to check out the shift register code, the PLC application used in this tutorial for yourself, just go and download my ready-made template by clicking on the link in the description below this video. Simply download the PLC application, follow the easy step-by-step guide, copy the UDT's library blocks and logic to your own application, and start building modular, scalable shift registers in TIA Portal. Thanks for watching and stay structured.